In this video, I will show you why computers do not understand decimal numbers, why decimal numbers work a lot better, and then show you how you can understand binary numbers yourself. Understanding these is the basis to understanding how computers store numbers and do maths. Hey everyone, welcome to my channel. My name is Oliver and I am a last year computer science bachelor student. At the start of my studies, I struggled with some CS concepts, but over the years I have managed to build a deeper understanding of them, making it much easier for me to make progress learning. So we'll start off with why computers do not use decimal numbers. So computers nowadays use current for doing computations and storing data. The way this is usually done is that we represent a lack, or rather no data in a block as 0 and data in a block, or rather current, as 1s. This can be done with either a low current or a high current. But now we have the issue that we only have zeros and ones to represent everything that there is in a computer. And an obvious issue is here that with numbers, we've always worked in a decimal system, also known as base 10. And here we have digits ranging from 0 to 9. But we don't have enough information in these 0 and 1s to create a 9. I mean, we don't have a 9. We have the 0 and we have the 1, but everything else is not there. So how would we encode numbers then? Well, it turns out that you don't need to use base 10 to represent numbers. You can, but there's alternative ways. There's several, however the one I'll be concentrating on today is binary, as you've probably told from the video title. So binary is called the base 2. It's called base 2 because we just have 2 digits to represent numbers. So we have 0 and 1. And this fits very well because these are, as you might see here, the same ones that currents can represent for us. So this is why the binary system is so fitting for computers. And this is also what's being used as computers traditionally, most of them at least, the ones that you use, only are able to represent zeros and ones. So how do we work with them? Well, first of all, I'm going to show you an example of a binary number. Then I'm going to show you how you can convert this into a decimal number, which you will more easily be able to comprehend. And then I will turn it back into a binary number so you see that it is the same number. We're going to do this with the binary number 1, 0, 1, 1. I will write a subscript 2 here so you know that this is in base 2. And when I write a decimal number like 371, I will write subscript 10 so you know that it's a decimal number. And you see that I've just used 1s and 0s. This is as we only have 1s and 0s for our representation. So if I wrote a 2 here, for example, or a 3 up here, this would not be a binary number. Okay, let's get into how you calculate this into a decimal number. So first of all, I want to show you that this is very similar to how decimal numbers work. As for example, if you have the number 371, in base 10, what is actually happening here is we have, also this is more easily represented by saying the number. Here, let's actually add an extra 8, just to make it even more sensible. This 8, it's 8,000. 8,000 means we have 8 different instances of 1,000. So what it actually means is 8 times 1,000. This 3 here just means we have 3 instances of 300. Right? The number is called 8,300, so it means we have 8,000s and 300s. And the 7 here may be in speech not as comprehensible since it's 70, but it actually means 7 tens, so 7 tens. And this 1 is just 1s, so 1, 1. If we write this with powers, you can see why this system is called base 10, as for 8 times 1,000, we can just rewrite this as 8 times 10 to the power of 3, as 10 to the power of 3 is 1,000. And we can rewrite this 3 times 100 as 3 times 10 to the power of 2, 7, as 7 times 10 to the power of 1, and this 1 as 1 times 10 to the 0, as 10 to the 0 is equal to 1. And so you can see that we always use this 10 in our representation, now in this decomposition, as I've drawn it here. And we use the digits as they are originally placed in this, as what's being multiplied with these powers. So 8,000, 300s, 7 tens, 1 1s. And the same can be done for base 2. So this time I will work from this representation upwards for base 2. So starting at 1011, we will start on the right side as it's easier to start. In the decimal format, we would, for example, have this 1 here turn into 1 times 10 to the 0. Starting on the left side would be more difficult because this 8 is being multiplied with whatever this is in the position. So this would be the third position if we start here with 0, here 1, here 2, here 3. So I will start from the right side as I find it more easy to start with. So what we do here, we know this is position 0. So what we're multiplying is 1 for this digit that we have here, then times 2 because we're working in base 2, and then to the power of 0 as this is in position 0 of this number. Here, for example, we would then have this be position 1, this be position 2, this be position 3. In the example for decimal, we would have the same here. And you can see this 3 here comes here, this 1 here comes here, and this 0 here, here. So we'll just copy this format exactly how we see it above. With this 1, we do a multiplication. Let me separate this a bit more. Here with this 1, we do 1 times 2 to the power, and then we know it's digit 1, so here 1. With this 0, we can write this, but because we're multiplying by 0, it ends up being nullified anyway. So 2 to the power of 2. And then this last one, which is to the power of 3, is 1 times 2 to the power of 3. Now, if we take this and we add it all up, we will get our decimal representation. So, starting from the left side here, I will not write these 1s as they will just mean that this number is added, and I will not write the numbers where there's a 0 as these just don't get added. So the way this would look is we would have 2 to the power of 3 added to, and then we don't write anything because this would be 0, 2 to the power of 1, this is the next non-zero entry, and then plus 2 to the power of 0. When we calculate these powers, we see that our result is 8 plus 2 plus 1, and this yields us the number 11. And this is in decimal representation. Now, what we're going to do is do the opposite operation so we can calculate what the binary representation is, which should yield us this again. The way we do this is we take the number we want to convert into binary, which is 11, we divide it by 2, and then see what the remainder is. So we get the quotient 5 and the remainder 1. I will write R for remainder and Q for quotient, and D for the division we're doing. Then with this remainder here and our quotient here, we take the quotient and put it into our new line and continue this process. So we write our 5 here, now divide this one by 2, and we get, again, remainder 1, and this time for the quotient we get 2. And we continue this process again, so we do 2 divided by 2, which gets us quotient 1 and remainder 0. And then one last time we take this 1. 1 divided by 2 gives us quotient 0, as 1 is not divisible by 2. And then our remainder is 1. Now once our quotient is 0, it means we have finished and we get our result. When Q is 0, we can read our result from the R column. And we do this by starting from the bottom to the top. So in the first position, that means we would have our 1. In the next one, our 0, then 1, and then 1 again. It means our result here is 1, 0, 1, 1 in binary representation. And now, if we look, we see our result here is the same as here. Or rather, what we started with and turned into our decimal representation of 11, we've now turned back into our binary representation of 1, 0, 1, 1. Now, there's a lot more with binary numbers that I will not get into now. I just wanted to make a quick starting video. But if you're interested, what you can do with binary numbers is you can enhance them, or rather expand them, by negative numbers. So currently we've just seen positive numbers, but you can also represent them as negative numbers, as well as you can represent real numbers. Now this was just some basics to binary numbers. However, you can work with these in other ways as well. You can do addition, subtraction, you can have negative and positive numbers. You can even have half numbers. So You can even convert the number 0.25 into a binary representation. This is a bit more complicated, and I will not get into this today, but it is something very relevant for computer science, and I might get into this at a later point. There's also other ways you can represent numbers. Binary is just one option. We've seen decimal, which is base 10, and binary, which is base 2, but you can practically do this with any number. One common way is base 1, which you might recognize as just ticking off numbers. So this would be a way to count in base 1. This would represent 6, 7, 8, 9, 10. Another common one is base 16, also known as hexadecimal. And for your information, base 1 is not used in computers a lot, but hexadecimal is used quite a lot. It uses the letters A to F additionally to the symbol 0 to 9. So you would have, for example, the number AF312. And this is a more compact way of writing binary, especially for addresses in computers. If you found this video helpful, consider subscribing for more computer science content. Also, let me know in the comments, what's one computer science topic that confuses you? I might cover it in my next video. Thanks for watching.